talking about the extreme value theorem, which says that given any if f is continuous on some closed and bounded interval, then it's guaranteed to attain, right? It must attain a max on AB, and it must also attain a min and a min on AB. Right? And we showed one way of doing it, which used the Bolzano wire stress theorem. And I said that I was going to give another proof, which gave sort of an alternate way of doing it. So just for fun, remember that the function is bounded. We already showed in the previous theorem that this function has to be bounded, right? Okay. So just like in the last theorem, let's let m be the supremum of all the values. We know that this set is bounded above, so it has an upper bound, least upper bound, right? By the least upper bound axiom. And we're hoping to find a place where this value is attained. Right? So let's do by contradiction. Suppose there is no place. Suppose there is no point where m is attained. Okay. That is, f of x is smaller than m for all x. We're going to do something funny. Let g of x, we create a new function, g of x, and that one's going to be 1 over m minus f of x. Okay. Notice that g is always positive. Right? G is always positive, right? Because this difference is always, m is bigger than f of x for all x. Okay. And the creation of, if you look at this g, examining this g basically does it for you. Can anyone tell me something about this g? Let's consider this g and see what you can get out of it. Somebody tell me something about g other than it's positive. Yeah, Valerie.
Should it be continuous?
It's continuous, right? Because it's 1 over a continuous function, right? 1 over a continuous function, right? It's certainly continuous. And this function never becomes 0. The denominator never becomes 0. So it's g is certainly continuous, right? G is a continuous function on e. Then it's bounded. It has to be bounded, right? Okay. Then it's bounded. Okay. Anybody notice anything else about this function? If you look at no.
Well, we told me how to define f of x is equal to m, right?
Right? It's f of x is never equal to m.
Yeah,
right?
that's what we want to achieve.
That's true. That's true. Yeah. We're hoping that that there's something wrong with this function. Okay, so let me ask you this: is it bounded? We said that it should be bounded, right? By by the previous theorem. It's continuous on a closed and bounded set, so it's going to be bounded. But let's think about it. Let's just look at the function itself. Is it a bounded function? Well, it's 1 over m minus f of x. M is the supremum of the values of f of x, right? So what do you know about the supremum? Well, what can we say about the denominator? This is the supremum of the values of f of x minus f of x. So
it's very small.
So it's very small. How small?
No, we can't bound it. We shouldn't be able to bound it.
We cannot bound it, right? Because f of x approaches m as close as we want, right? F of x can get as close to m as we want, right? Because this is the supremum. Remember the property of the supremum, right? We know that m is not attained. We're assuming that m is not attained, right? M is not attained, and so that tells us that for every epsilon, there's going to be some f of x between m minus epsilon and m, right? In other words, we can make this as small as we want, but that means that G is unbounded, right? So in fact, G is unbounded, right? So that's a contradiction. But in fact, G is unbounded.
Why does proving that it's unbounded prove that M is contained in?
So we're doing proof by contradiction. Suppose that there's a missing word here. Suppose there's no point where M is attained. Suppose that.
Yeah, I understand. I just don't get why that. It's just because we prove that, like, this function.
We show that the function is bounded, and we just show that the function is unbounded. So it's a contradiction. There's a logical contradiction. So we said, well, suppose there's no point where the supremum is attained. In that case, you create this function. This function is bounded, but the function is actually unbounded, and so you have a contradiction. You can do this in another way. In my notes, I actually have it in a different way. So let me just hold on for a second. Okay, so I have in the notes like this. G is continuous on AB. Let's do it over here. So let G of x be 1 over m minus f of x. Right? Notice G of x is positive. So G is continuous on AB. And so G is bounded, right? There exists K such that G of x is less than K for all x. And you're just you go along that line a little bit farther, and you see what happens. In that case, that's the same thing as saying that 1 over m minus f of x is less than k. Right? So what does that say? That says that 1 is less than. Let me turn it over. Sorry. M minus f of x is then greater than 1 over k. Right. And that tells you that f of x is less than m minus 1 over k. Right? What's wrong with that? Why is, and that, so that gives us a contradiction. How come? Mia.
Because he said M was the supreme.
Exactly. Yeah, m should have been the supremum, but instead we found an upper bound that's smaller than the supremum. Right? So contradiction. Okay. So either way, you're going to end up with some contradiction, and so you know that there must be some place where the maximum is attained. And similarly, you can do this for the minimum. So similarly for the minimum. So that's the end. Okay, any questions? Any questions? Okay, so, okay. So next we're going to do the intermediate value theorem. Intermediate value theorem, which is another one of those results that you see in calculus, but is never really explained to you, or it's explained to you, but maybe not rigorously. So, and it turns out that this is also by Bolzano. I didn't realize that. Okay, so you have some function, right? So who can tell me? I'll just ask you. Who can tell me what the intermediate value theorem says? What's the intermediate value theorem? You know what it is. Yichen, what is it?
I think if you're continuous,
Yeah.
A, B,
The open interval or the closed interval?
let's say it's close first.
Yeah, it's close. It's close. Yeah. Yeah.
And so the fx is contained in fa and fb. Oh, no, wait. So you can find a c between a and b such that fc equals something.
Can find a b. Can find a c between a and b such that something happens. Something happens. Yeah. Okay. So what is that? What is that something that happens? Or what's the picture? A, B, say. You have a continuous function. There's a C where something happens.
F of A is less than F of C, or less than or equal to F of C, which is C.
F of A is what? Less than F of C?
Which is less than F of B.
Less than F of B? So there's a... Does anyone remember the intermediate value thing? This is part of it. Okay, so it goes like this. Okay, so let gamma be any value between f of A and f of B. Right, let gamma be any intermediate value, right? Some value between the values of the two endpoints. Then there exists a C where f of C actually attains that gamma. Yeah, Mia.
Is it in the open interval AB because it can't be equal to A or B?
Right, right, it's not going to be, it's not going to be at A or B because gamma is not f of A and gamma is not f of B, so it's not going to occur at the endpoints. Does that make sense? Right. So your picture is like this, right? You've got two values. Oops, there's A, there's B, f of A and f of B, right? And what this is saying is that if you choose any intermediate value, then there's some place where you attain that intermediate value. Right? So, I mean, in English, it's pretty straightforward. It's saying that if there are two heights here, and you choose any intermediate height, then there's some place where you cross that line, right? It may be that you avoid it for a long time, but at some point, you're going to have to cross that line, and you attain the value as you cross the line. Okay, so you pass through it. Okay. Here's the proof. Actually, let me make it clear that this is not completely obvious. Let's see. Suppose I have something like this. Okay, this length is 1 and this length is 1, and this is a right angle here. Okay? And suppose that we're back in the days of the Greeks. So this is the rational numbers, and this is the rational numbers also. Okay? These are rational numbers, and here's a line like this. Okay? So, is there any place in this world, is there any place where we intersect the axis? Is there any point where you intersect the axis? No. No, there isn't. We never intersect the axis. Right? There's actually a hole there, right? Because this length is √2, there's actually no number there. Okay, so although it may look like you've got a complete line here, in fact, there's a lot of holes in the rational numbers, and we never cross the line. There's a hole there. There's no place where we hit the value 0. Okay, but the real numbers don't have those holes, and so when we have a continuous function like this, then we actually do intersect. So this is a continuous function. This is a continuous function on the rationals, but it has a hole. Yeah, John.
Why is it a Bolzano?
Because it was made by Bolzano.
Well,
Yeah, he's just the person who discovered it, I guess. Okay. Okay, so here's the proof. Suppose f of A is f of B, just it could be the other way around. Suppose, without loss of generality, that f of A is less than f of B, and let gamma be in between them. And consider the set E, where E is all the places where the values are less than gamma. Okay. So the picture is like this. You've chosen your gamma, right? right? You've chosen your gamma, and you're looking at all of the x where f of x is less than gamma. Okay. So here's gamma, and I'm looking at the places where f of x is less than gamma. Okay, so all these, this is part of E. And this is part of E, right? These two sets together, these two intervals together make up E. Right? You're looking at all points where the outputs are less than gamma. Okay, and maybe you can guess what we're going to, what are we going to take as the place where f of x equals gamma? We're going to take it, we're going to make it from E. What's it going to be? Can you see from the picture? Okay, let's see. We'll take the supremum. Let C be the supremum of E. That will be the place. We'll see that that's the place where gamma is attained.
What if it's greater than gamma? F of x is greater than gamma?
What if f of x is greater than gamma?
If you take a supremum of E, what happens?
Say it again?
If you take a supremum of E,
Yes.
does it, you said you will be able to attain gamma.
That's where, so we're hoping that the supremum of E, so the supremum of E is going to be this point here. In the picture, the supremum of E is this point here.
Oh, okay.
Okay, and we're hoping what we're going to see is actually that is where gamma is attained. That's where we cross the line at the supremum of E. Okay, so the only thing that you can be worried about at this point is there actually a supremum, right? Okay, but you know that this set is contained in AB, and so its upper bound, it has an upper bound of B, right? At least you know that B is not in the set, right? B is not an element of E, right? And you know that, what do you know about A? A is an element of E or is not an element of E? So E is E is the set where the outputs are all less than gamma.
Okay, yes.
Right. So A is an element of E. Okay. A is an element of E. B is not an element of E. Right. So we know that we know E is not empty, and we also know that E is bounded above by B. Okay. So it does have a supremum. Okay, so so there exists a sequence called Xn in E, such that the limit of the Xn equals C, as n is infinity. So take a sequence x1, x2, x3. Blah, blah, blah. So the sequence is inside your E set and approaching the supremum. Okay, so this point is C, right? And you take some sequence inside of E, inside of your set that approaches C. So, right, since C is since C is the supremum, right? C is the supremum, so we can always play this game of there's somebody in the interval C minus 1 over n, comma C, right? Call that guy x of n. Right? So we know that the interval C minus 1 over n, comma C, intersects the set in this line. Call any point, pick a point, and xn in that intersection. Now, on the other side, choose a sequence Tn that's in AB outside of E. Okay, such that Tn converges to C. So here's our C, here's B, here's A. You can choose some sequence, right? Just choose some sequence inside here that converges back to so T1, T2, blah blah blah, converging to C from the top. Okay. So you could say you could take Tn to be the minimum of C plus 1 over n comma B. Okay. So it basically looks like, C plus 1, C plus a half, C plus a third, etc., etc. Those guys are converging down. So then, f of xn for each n, f of xn is less than gamma, and less than or equal to f of t sub n. Okay. What happens to, what can you say about the limits? So let's take the limits. Take the limits. Okay. Let's do the right limit first. What can you say about the right side limit? As n goes to infinity, what do you get?
C.
You get f of c, right? Yeah. Right.
Oh, f of c.
Because the tn go to c, and this is a continuous function, right? Okay, so f is continuous. And the same thing happens on the left, right? The limit of x of n also, as n goes to infinity, the x of n also go to C. Right. So by continuity, you get this, right? So what is that saying? Right? We have this thing. F of xn is less than gamma, right? And we also have gamma is less than or equal to f of t of n. Right. If you take the limits, what you get is that. So this part is an exercise. So f of x of n is less than gamma. When you take the limits, what you get is that the limit of f of x of n is less than or equal to gamma. Okay, so I'm going to, this part actually needs a little bit of proof, but I think you can probably do it. If you have any sequence like this, when you take the limit, you're going to get a less than or equal to. Okay, and then on the other side, we have gamma is less than or equal to f of t of n, and when you take the limits here, you get it's already greater than or equal to, and that greater than or equal to just gets preserved in the limit. Okay, and so what you get is that this is f of c, and this is f of c, right? But that gives you that f of c equals gamma. So f of c equals gamma. Any questions about this? Right, we're trying to find the place where f attains the value gamma. We look at the set where f is less than gamma. Okay, take the supremum of that set, and then take a sequence within the set that converges to that supremum. Okay. Also take a sequence outside of that set that converges to that point. Okay. Now, when you take the limit of the sequences, you see that the limit of one sequence has to be less than or equal to gamma. The limit of the other sequence has to be greater than or equal to gamma, right? But the limits of those sequences are both f of c. So f of c has to be less than or equal to gamma and greater than or equal to gamma, and so it must be equal to gamma. So maybe the only thing that's not completely clear is this thing that I put as an exercise, right? If you have some sequence, if f of some sequence is less than some value, then the limit of that sequence as it goes to infinity has to be less than or equal to that value. So that's the exercise, right? Given any sequence, given any convergent sequence. Sorry. If all the values are less than y, then the limit of it must also be less than or equal to y. Okay. So that's actually a pretty easy exercise, and I leave it for you to do. Okay. There's actually another point where I've swindled you. Okay. There's another point where I've actually lied to you. Can anyone, and I really erased half of the board, so it must be on the other half of the board where I lied. Can anyone catch where I'm kind of cheating you? Let's go through it. Right. Suppose f of a is less than equal to f of b, that's okay. Let gamma be in between it, that's okay. Consider this set where everything is less than gamma, that's okay, right? Let C be the supremum. We know that the set's not empty, the set's bounded above, so it's bounded above, it has an least upper bound, that's okay. There exists a sequence x of n in E such that the limit of x of n equals C. And I say we knew this to be true, blah 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 blah. Is there anything wrong with that? There's something a little bit wrong right here. Okay. Anyone see it?
Do we know that x of n converges?
Well, by construction, it will converge, right? Because we've chosen, you can choose the x of n in this interval, right? In c minus 1 over n. So the length of the interval is 1 over n, right? And so you know that the distance of x of n to c is less than or equal to 1 over n. So the x of n's do converge, if the x of n's actually exist. Okay. And so the thing that I'm cheating you on is, how do I know that, why is C not an element of E? Why is C not an element of E? Because this sort of game, remember we said we could do as long as the supremum is not an element of the set. Right? If the supremum is not an element of the set, then we can play this game. Right? So how do you know that C is not an element of the set? I'm going to leave that as a puzzle. There are two ways of thinking about it. It's actually impossible that C would be an element of the set. And there are two reasons why, but I'm going to let you think about it. Maybe on your homework. Ichen, you look like you have an answer. Do you have an answer?
Oh no. But because the conclusion FC will equals gamma, but how we construct E is the contains gamma.
Right.
That's not the conclusion.
Right. Yeah. So, we needed to construct that sequence, right? But actually you're headed along one of the lines that I was thinking of. So you could say, well, look, we basically ran through this argument and we saw that f of c equals gamma, so c couldn't have been in E, right? But as you say, don't we need to construct a sequence? Didn't we need to construct a sequence? And you could say, well, no, we don't need to construct a sequence. Why not? Right, so here's each-n's path. Okay, each-n says, well, let's suppose that f of c actually is less than or equal to gamma. Say f of c is less than or equal to gamma, right? In other words, so say c is in the set. Okay. In that case, f of c is less than or equal to gamma. Right? Do we need that lower sequence anymore? What did we use the lower sequence for? We used the lower sequence to show that f of c was less than or equal to gamma, right? But if c is in the set, then f of c is less than or equal to gamma. We don't need the lower sequence. Okay, and then use the upper sequence to get that f of c is greater than or equal to gamma. And that means that no. I'm sorry. We would get this. If c is in the set, then f of c is less than gamma, right? Because that's what it says. Sorry. But then we get that f of c is less than gamma and greater than or equal to gamma, which is a contradiction. Okay, so that's impossible. Okay, good, Jen. Sort of. Yeah, at least you saw the possibility. Okay, so yeah, I guess no, it's not going to be on your homework because we've already answered it. Okay. So why isn't it? Because it cannot be. Okay, last part of the lecture today. Is something that you may have seen as a homework problem in your calculus class, which is called Brouwer's. Well, this is one tiny version of something called Brouwer's fixed-point theorem. So it goes like this. Suppose you have a function that goes from AB to AB. Okay, so it's on some interval, and its outputs lie in that interval. Okay, so basically it lies in a square. Okay, and suppose that it's continuous. In that case, f has a fixed point. In other words, a point C where f of c equals c. Okay, I'll give you 1 minute to think about it. See if you can come up with a picture or a proof why this is going to happen. Me, yeah. Do you have an idea? Okay, hold on.
Hold
Hold on.
on.
Yeah, hold on. You go ahead, Nina, I'm sorry. I should have just let you talk.
Is it that the function has to cross the x equals y line?
Yeah, look, right, here's this x equals y line. And basically what we're saying is that it has to cross the line at some point, right? It has to cross the line at some point. If we start in this corner, we've already touched the line. If we end up in this corner, we already touched the line, right? If we don't start in this corner or end at that corner, then, well, at some point we've got to cross the line, right? And that's basically the proof of it. So suppose f of a equals a, then we're done. Or f of b, or f of b equals b, then we're done. So that's case one. Case two, suppose f of a is not equal to a and f of b is not equal to b. Then consider g of x being f of x minus x. G of a is less than 0. Wait, greater than 0, sorry. Greater than 0. And g of b is less than 0. Right? Because f is bigger than the line f is bigger than the line at the beginning, f is lower than the line at the end. Right? But that means that there exists a place where g of c is equal to 0. But that's the fixed point of f. Right? F of c. There are funnier versions of this in higher math. I think if you have a map on disks, then there's always guaranteed a point that's preserved by the map. If you have a continuous map on disks, then you're guaranteed a point where the map doesn't move the point. Right? And then there's something called the Hairy-Ball theorem, which is like you have a three-dimensional ball, and then you have all these like hairs on it. These things are actually vectors, but it's called the Hairy-Ball theorem because it looks like a ball with hairs on it. Okay. And the theorem says basically that if you try to comb the hairs, you're always guaranteed that at one point the hair is going to stick straight up. That's the Hairy-Ball theorem, and it's related to this Brouwer's fixed point. There's no way to do it. There's no way to comb everything flat, basically. Or to even make it, like angled. You'd hope that you could at least get them all of them slightly down, but it's impossible. There's always going to be one that sticks perfectly straight up. But for that, you have to wait for a course in algebraic topology. It's actually a pretty hard thing. Well, it's not a hard thing, but it's a high level course. Okay, that's it for today.